All right. So we're still under quarantine. This is our first Calculus BC. We're going over polar equations today, so I'm going to look at a couple new things as far as vocabulary goes with shapes of various polar equations. And then all of our old stuff with area and arc length. We'll finish off with one free response question as fast as we can. And again,
Mm-hmm.
you've got kind of a lot of practice problems up on course sites. So I want to keep this to about 15 to 20 minutes if we can.
Mm-hmm.
Okay, so starting off with the easier ones, which are circles. There's nothing new as far as vocabulary goes for circles, but I just wanted to point out that there's several different ways that we can create a circle with polar equations. So you could just throw a radius up. So if you've got any constant number, you'll end up with a circle centered at 0, 0. But if you don't want to center at 0, 0, you could use sine or cosine, and you'll end up with different circles. So anytime you've got an even number times cosine, you'll end up out here to the right, so kind of like this 2 cosine theta. If you've got a negative even number times cosine, you'll end up to the left. If you've got a positive even number times sine, you'll end up above it. And a negative even number times sine, you'll end up below it. Okay, these ones might be new. So a limacon is a shape that looks like a lima bean almost. So these are not technical terms, this is just what I think of in my head. A lima bean is, it's like a popular bean to eat for vegetarians in the US, but it looks like a bean. So if you see the word limacon anywhere in your AP exam, they're talking about one of these three shapes.
Mm-hmm.
The general form is a plus b sine theta. If a over b is between 1 and 2, then you'll end up with this kind of smooth bump on the bottom.
Mm-hmm.
If a over b is exactly 1, you end up with a sharp cusp. And if it's less than 1, you end up with an inner loop and an outer loop. I've seen College Board refer to this as the inside loop and the outside loop, or the inner loop and the outer loop, when they're asking you to find the area. So if you see it, that's what they're talking about.
Yep.
Any questions on shape or vocab for this one?
No, but is there any question asking about the shape like this?
I don't think they'll ask you for the shape directly, but if they tell you it's a limacon, they assume that you know what shape they're talking about.
Oh, okay.
So if they say, find the area of the inside loop of the limacon, then you know your shape is going to look like this, where there's some overlap. So the easiest way that you could do that is because if you notice these limacons are all passing through 0, 0 for that inside loop. You can set this equation equal to 0 and solve for the first 3 times that it hits 0. Your shortest distance between those 3 points will be your inner loop, and your longest distance between those 3 points will be tracing this outer loop. If you do want to trace the outer loop, so you just want the outer area, because your radius will be tracing all of this inside area, which includes the inside loop, you'll have to subtract the inside loop in order to get the outer area only. Okay, next shape. Lemniscates. I think of these as skate tracks or race tracks. There's no special vocabulary with them, but if they do tell you that your shape is a lemniscate, then you know that you've got this kind of figure 8 shape going on. Okay, I think I might have lost you. Are you still there?
Yeah.
Oh, okay. So general form for this is r squared equals a squared times your trig function times 2 theta, or of 2 theta. If it's positive with cosine, you're going horizontally. If it's negative with cosine, you'll go vertically. If it's, oops, I wrote this twice. This one should be
Oh.
negative, actually. Break out and fix that. Sorry about that. So, if it's positive with sign, we'll end up in this first quadrant. If it's negative with sign, we'll end up in the opposite quadrants. I think if I was asking for the area of these, I might say find the area in the Lemniscate that's in quadrant 1 and 3. Or something like that. Okay, then we've got spirals. Anytime you've got a constant number times theta, you'll end up with this crazy looking spiral shape. But if you see the word spiral, this is what they're talking about. I believe that's our last shape. Oh, no, one more. Roses. Most important one. Okay, so if you see a rose, you'll end up with a shape that looks like this. If your n number is odd, then n is the number of petals. But if n is even, then 2n is the number of petals. So for this shape that I drew right here, this n would actually be 2. And you end up with 4 petals because it was even and it doubles the number of petals. Whereas for this one, my n is 3 and I end up with 3 petals. Okay, be careful with your roses, especially for these odd number roses, because it is possible to trace the entire shape in pi instead of in 2 pi. Which we'll see in a minute can get a little bit confusing when you're trying to find the area. Okay, really quickly, polar area. We came to our polar area equation by looking at our area of a sector. Our area of a sector, we could say that the angle of our sector compared to the angle of the entire circle would be theta over 2 pi. So that's theta over 2 pi times the total area should give us the fraction area that is the sector length. So the area of a sector is 1/2 r squared theta. And then using that, if our r is constantly changing, then this would be an infinitely small change in theta, and we'll just be tracing a bunch of really small sector areas, infinitely small sector areas, until we add them all up in order to get the shape we want. So our sector area, as we keep going through, would be the integral from a to b of 1/2 r squared d theta. You've seen this on your formula quiz, is 1/2 integral from alpha to beta of r squared d theta, which is the same thing, we just simplified. Any questions on area?
Nope.
Okay. Moving fast, this is our review. Polar arc length. The idea here is the same as our distance formula, so Pythagorean's theorem. If I had some sort of a change in y and a change in x, if I wanted to solve for the change in distance, we could use Pythagorean's theorem, which ends up being our distance formula, but we can use the same principle to figure out the actual distance of a curve in polar form. So I've got some sort of a change in x over theta and a change in y over theta, so my whole equation is arc length. It would be the change in length. So if I integrate that, my change in the distance, if I integrate the change in the distance, I'll get the arc length. That change in the distance would be equal to the square root of dx over d theta squared plus dy over d theta squared. So if I integrate both sides, I'll end up with this. So for the inside of this square root function, I've got dx over d theta squared plus dy over d theta squared. Since x is r cosine theta and y is r sine theta in polar form, I'll flash that really quick. So here's our polar form. We've got a radius and an angle. So if I wanted to solve for the components, that would be r cosine and r sine. So going back. So when you derive x, I would have product rule, and this would be r prime cosine theta minus r sine theta squared, plus r prime sine theta plus r cosine theta squared, so that's y prime. So I can combine these. If I do, when I go to square these, I'll end up expanding this, so it's a little bit long, but that's all one line. So after everything's expanded, things start to cancel. So point out really quick. Okay, if we group these, so right now I've got dr over d theta squared that I can put together. So for this term and this term. So if I group those, I can factor out my dr over d theta squared, and I'll end up with cosine squared theta plus sine squared theta, which is 1. If I group my terms that have r squared, the same thing happens. So here's r squared and r squared. So I can factor out my r squared, and I'll get cosine squared plus sine squared. And then these two terms, negative 2r times dr over d theta cosine theta sine theta plus 2r dr over d theta cosine theta sine theta, that's really hard to see, are the same term, so they'll cancel out directly. Okay, so that gives me, since I'm just multiplying by 1, r squared plus dr over d theta squared, or my arc length formula. Any questions on how we got there?
Nope.
Awesome. So here's everything in one page. We've got our area of the polar equation is from alpha to beta of 1/2 r squared d theta. Our arc length equation, the integral from alpha to beta of the square root of r squared plus dr of d theta squared d theta. And then if we need to convert to rectangular, we've got our components. Any questions on anything so far?
Nope.
Okay. Let me break out of this then. And we'll take a look at one more. Okay. I'm not sure how big this will be on your screen. Can you see what's going on?
Yeah, there are many ellipse shapes.
Right. So what I've got happening here is two different shapes, really. So I've got R1 is 4 sine 3 theta. So again, that's a rose with okay, so I've got a rose here. I've actually got another rose here for 3 cosine 4 theta. Our even number for n is going to double that number of petals. So as you can see here in blue, I've got 1, 2, 3, 4, 5, 6, 7, 8 petals is my cosine of 4 theta times 3. And then here when n is 3, we only have 3 petals. Okay, so my goal here is to find the area that's inside R1 and R2 in quadrant 1. So I'm going to zoom in here. Here's quadrant 1. And I want to find this shape here in yellow. Okay, so if I graph this in our graphing calculator, I'm going to do this in function notation first. Oops. And we'll go from 0 to 2 pi. I'll flash this just so you can see what I'm graphing, but I have 4 sine 3 theta and 3 cosine 4 theta, where the 3 cosine 4 theta, so that's our blue function here, is in bold. Okay, if I graph. Oops, I need to go a little bit higher, I think. Okay, there we go. So here's our sine function, and then in bold is our cosine function. So you can see each petal being traced out. This cosine function in blue, I would start at, the cosine at 0 is 1 times the 3, so I'm actually starting here. So if I wanted to trace this, my brush width a little bit bigger. If I wanted to trace this, my function is doing something like this for the blue function, so I'm going here. And then around each of these petals. For my sine function, I'm doing something like this. And I'm actually tracing twice. Okay, so we can see that in our calculator. For that sine function, here's 1, 2, 3 petals, and then it repeats 1, 2, 3. Okay, the reason why I'm graphing in the rectangular is because it makes it easier to see which the points here where we have intersections. So if I wanted to calculate this first intersect, I can go second, calculate and intersect. For my first curve, my second curve, and my guess I'm actually going to throw out here, so really close to 0. So I'm going to jump all the way back down and get an intersection point there. Okay, so there's my intersection point, so I'm going to call that A. And before I do anything else, I'm going to store that in the calculator. So second quit x store alpha A. So here is our point A. Which, double check, yep, we are in radians, so is in radians. Okay, if I wanted to trace this first part in yellow, what would I have to do?
We
Okay, I've got to integrate. Am I going to start with finding the red part or the blue part?
the blue part,
Okay,
the
so
red part.
okay, so if I start with the red part, then I could integrate, since this is a sine function, sine starts at 0, I could integrate from 0 to A, and that would get me all of this area that I'm tracing right now. Ooh. All of this area here in black would be tracing from 0 to A for the red function. Okay, then what?
And then times 2.
Okay, I think we are symmetric. But just in case, you could trace this blue function if we weren't symmetric, going from A until the first time that your cosine function hits 0. You'd also be able to hit there, although I believe you're right that this will end up being symmetric for this. I'm not exactly sure.
Oh, so then the other way is we trace blue function.
Right. Okay, so I'm going to make this, here's area 1. Okay, my area 1 then, so far, is 1/2 integral of 0 to A of our red function, so that's R1. Okay, plus 1/2 integral from 0, not 0. 1/2 integral from A
to 0.
Yep. So we need to know when that function's going to hit 0 as well. So I could solve this by hand by setting this function equal to 0 and solving for the first time that this cosine function will hit. I guess I'll do that just for the sake of it. So this will be 0 equals 3 cosine 4 theta. If I do, this is 0 equals the cosine of 4 theta. Where is the cosine normally equal to 0?
Pi over 2.
Okay, so normally at pi over 2 and 3 pi over 2 and a couple others equals 4 theta. So I could divide everything by 4 and I would start getting my angles. That's pi over 8 is the first time that that's going to happen. And 3 pi over 8. And then every... I'm going to have pi over 8 plus pi fourths times n will give me another point where we hit 0, right? Okay, so this is from A to pi over 8 of r2 squared d theta. Okay, So that's my area 1. Then how do I need to find my area 2? Or how can we find area 2?
So we find the point.
Okay, if I'm looking for the intersection point, would you want to look in your calculator in the polar or the rectangular?
Rectangular.
Rectangular, okay, so here's our rectangular again. I've got a lot going on here. How can we know which intersection we want?
Isn't it the second intersection?
Okay, so it is going to be the second time we're tracing that red function. So if I look at this, this is our first petal, second petal, third petal. So for our blue function, I'm tracing petal 1, petal 2, petal 3, petal 4, petal 5, petal 6. This is when we actually come up. So petal 1, 2, 3, 4, 5, 6. So we're in the middle of our 6th petal. Count that again. 1, 2, 3, 4, 5, 6 here. So my intersection's right here. That we need for the other one. I'm gonna just double check. So that's the 1, 2, 3, 4th time I'm tracing my red function, which makes sense. So that would be my first petal for the second time we go around. Okay, so second calculate and intersect. With my first curve, second curve, and my guess this time way out here. On that 6th petal for the cosine function, 4th petal for the sine function. Gives us another intersection point. So again, first thing I'm going to do is quit out and I'm going to store this. So x store alpha b. That way we don't have to round or anything. Okay, if you're on your AP exam, I would copy all of this, but then just cite that as b, so b equals all of this. And then from that point on, you can just write in your notes that that angle is b. So if I'm tracing this, am I tracing the blue function first or the red function first?
Red one?
Okay, so if we trace the red function first, my red function will be coming out this way, right? So my red function would go from B until the next time that the red function hits 0. Okay, so that's actually, if I trace this out, from here all the way down to here, right? So it's actually the second half of this, that's right. So I'm just going to write that over here in the second half. Okay, so second half of this is plus 1/2 times the integral from b until the next time that we hit 0 for our sine function. So I'm going to jump back into our calculator again. Our sine function is hitting 0. How often? So when is our sine function normally equal to 0?
Pi, 2 pi, and so on.
Okay, so 0, pi, 2 pi. If I divide by 3, then I'll get every time that it would hit 0 for this function. So that's my angle. So that would be at pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3 would be the end of this 4th petal. So I'm going from b until 4 pi thirds. This is my sine function, which is our r1 squared d theta. Okay, and the last part of this, I need the area for the first half of A2, would be what?
1/2 0 to B.
Okay, from when we were at 0 to B, and this is the 6th petal of our cosine 4 theta. So I'm going to keep expanding this a little bit. So this would have been 3 pi halves, 5 pi halves, 7 pi halves, 9 pi halves, 11 pi halves. 1, 2, 3, 4, 5, 6. Okay, that's all we need. Equals 4 theta. So I'm going to divide by 4. And that'll give us, eventually, the 7 pi over what?
7 pi over 8.
8. Okay, so 7 pi over 8 is what we need here. Okay, again, if you don't want to count just following your curve, I can count on here. So this was the first petal. So this is the first 0, second 0, third 0, fourth 0, fifth 0. Ooh, I actually got the wrong one there. 1, 2, 3, 4, 5. Okay, I actually need this 9 pi over 2, so this should be 9 pi over 8. Oops. Great, again, 1, 2, 3, 4, 5. Okay, first time would be 1, that's after the first petal, okay. So my 5th time I hit 0 will be the start of my 6th petal. Okay, and what goes in here?
R2 square.
R2 squared d theta, perfect. Okay, so my final answer is this. And if I did want to find it in the calculator, right now my R1 is Y1, my R2 is Y2. So we could start typing out our integral with something like this. So this is 0.5 times math 9, the integral of variables, y variables function y1 squared. From 9 pi over 8 to b in terms of x. Oops. Okay, what did I get wrong? Oops. Got my order wrong here, I think.
Oh.
Not used to the 83s anymore. Alright, there we go. So for our older calculators, that's equation, variable, lower bound, upper bound. So y1 squared in terms of x from a to b. Okay, so I can use that format and just do that for all of our areas, add them together, and I should get my final answer. Any questions on our process?
Nope.
Okay. I'm actually going to end there, I think, because they're right at the 30-minute mark. You've got a handful of free response questions that are up on course sites. I will send them on Skype as well as another set of multiple choice questions. I think there's maybe 15 to 20 multiple choice, but they're faster than the ones from physics, so it'll end up being about the same time. So I'm shooting for about an hour. Alright, anything else we need?